All right, okay. So now we'll hear from Alexander Shosten, I almost said that correctly, about browser extensions, how we can probe them through JavaScript, and how we can protect against these attacks. So the floor is yours.
All right, thank you. I'm going to present some joint work with Steven Van Acker, Pablo Picasso Sanchez, and Andrew Sabelfeld. And we're all from Chalmers University of Technology in Gothenburg, Sweden. So the first thing we need to understand is basically what is an extension. So just real short, extensions allow users to modify the browser behavior. And these modifications can be anything from blocking ads, to blocking tracking scripts, to serve as a password manager. Basically, whatever you want, there is most likely an extension that can do that for you. It's small applications written in a combination of JavaScript, HTML, and CSS, and we can slightly simplify, divide them into two parts. We have the content scripts, which is what will actually communicate with the shared DOM, with the web page. And then we have the background scripts. And the background scripts, they have access to elevated APIs. They can, for instance, read network traffic if they ask for that permission. And the user grants an extension permission when they install the extension. Extensions can also inject content into this shared DOM with the web page. One way of doing that is through what's called web accessible resources, which means that you flag certain resources as web accessible, and then they are allowed to be injected. And there are Chrome extension URLs for Chrome and Moz extension URLs for the new Firefox one. So these web accessible resources, they can be used to help detect extensions. So for instance, you can detect the Google Cast extension by querying that URL. And then the extension can discover your Chromecast on the same network, and you have a nice, seamless communication from the web page, potentially, to your Google Cast. And note between the slashes is something that just looks like gibberish, and that's the extension ID. And for Chrome, that one is fixed, which means that we can always make a request to a known resource for an extension from the web page. And if that extension is installed, we will get a resource back, which means that we can probe every single extension that has a web accessible resource. And this is not optimal, not according to Mozilla, so they changed their ways of doing it. Instead of having an actual extension ID, they randomize it. And this randomization, it's generated for every browser instance, because that would prevent websites from fingerprinting a browser by examining the extensions it has installed. And Chrome felt like this might be a good idea. So developers have mentioned that that is something that they want to implement into Chrome as well when they have the opportunity to make a breaking change. But this was a couple of years back, and they still haven't done it, so maybe they've changed their minds. So based on what Mozilla is doing, we can no longer just probe for extensions. But if we monitor our own DOM and we see a URL like this, then that means an extension has injected some sort of content. Then we can pre-compute offline a mapping from the resource to all the potential extensions it can be. And then for using this recently acquired random ID, we can then probe for unique resources within each of the subset of extensions. And if that extension is installed, that resource will indeed be returned, which means that we can de-randomize extensions in spite of this randomization scheme, as long as they just give us the random UUID. So we want to figure out how many extensions are actually susceptible to this kind of revelation attack. So we download all extensions for Chrome and Firefox, and then we filter out the ones which might inject content. And this is based on two things. One, they must have at least one web accessible resource declared, and they must call a function to get this random UUID. In Mozilla or in Chrome, it's enough that they somehow hard code their extension ID into a URL. Then we can check for each extension if they have at least one unique path to a resource. And we can also check if they have at least one resource with unique content by hashing the content. And then we take the union of these two sets. And it turns out that for Firefox, roughly 1,400 extensions might inject content. And based on that, almost 94.4% of all of those extensions would be able to be de-randomized. As long as they inject one single resource, we can de-randomize them. Similarly for Chrome, it's almost 90%. And in total, it's a little over 90% of all extensions for the two biggest browsers. So this random UUID, it's not really optimal, but they mention that it's being created per browser instance. So then the question is it easy to regenerate it or to reset this random UUID? And it turns out that it's not really easy. It's not really doable. For Windows, when you reinstall the browser, it actually works because, for once, Windows have the default setting that they want to restore the everything when they discover that you are reinstalling the browser, and then they want to remove all the old add-ons. And if they do that, you have to reinstall them, and if you reinstall them, you will get the new ID. For Linux and Mac, that is not the case. You need to manually go in and remove the profile for that to happen. Similarly, when reinstalling the extension, unless you restart the browser between uninstalling the extension and then installing it again, you will have the same random UUID. And clearing the profile will basically delete all your installed extensions. Then you have to reinstall them, and then you will get a new random UUID. But none of this is really ways that we want users to have to do if they want to have a new random UUID. So then the question is, how many extensions actually reveal themselves? So this is from the manifest file of an extension, which specifies what files belong to the content script that will be active against the DOM. And the content script has this matches clause. And that's a list of regular expressions. And if the visited URL matches one of those expressions, the content script will become active, and the extension might inject something. Unless it matches something from the exclude matches, because then it will remain dormant. So we use these manifest files to derive three sets of URLs. One is the real URLs, which we derive from this matches attribute for the content scripts. Then we have attacker host URLs, where we just replace the host name with attacker.invalid. So example.com/abc becomes attacker.invalid/abc. And similarly, we also have the by DNS URLs. If you have, for instance, star.com/abc, naturally attacker.invalid/abc will not trigger that extension in any way because it will not match that regular expression. So then it's basically an attacker might have to buy a host name for it to become active. We then extract all the regular expressions from the extensions, and it yields in total roughly 24,400 regular expressions out of the 13,000 extensions. And then we crawl, where we use the common crawl database. It has roughly 4.5 billion URLs. And the reason why we use the common crawl database is because we want actual URLs to match these matches attributes. And then for each regular expression, we only consider the first 100 matching URLs. And since an extension can have more than one regular expression, we just take a random set of maximum 1,000 URLs for each extension. If the extension doesn't have 1,000 URLs in total, we will just take the full set of URLs. So it turns out that not many extensions actually are dependent on the structure of the DOM for them to inject content. The content-dependent part is the ones that required a certain structure of the DOM, where the any content basically meant that they injected their content onto a blank web page, where only the URL was the only thing that mattered. So in total, we got 222 Firefox extensions to inject content, which, if we assume no overlap in the users between the extensions, would potentially be 792,000 users. And the problem with this is that each one of those would be uniquely identifiable just based on this random UUID, which is not very good. So we have a perfect tracking for those users. And then we redo this where we check for unique path and unique content for each of the ones that injected content that we discovered. And it turns out that a little over 97% of all those extensions that injected something, we can de-randomize completely, which means that the random UUID does not really serve its purpose. Similarly, a little over 97% for Chrome as well, and in total, a little over 97%. So how can we try to mitigate this? We propose a whitelisting mechanism that is based on two whitelists. One to help solve the probing attack, one to help defend against the revelation attack. So the probing attack, that is the web page that initiates it, which means that we have a whitelist that says what web pages are allowed to access what resources or what extensions. So if example.com were to try to access extension B, that would be blocked. Similarly for the revelation attack, where the extension are the ones that initiates it, then we have a whitelisting that says what extensions are allowed to execute towards what domains, or are allowed to inject content into what domains. But this is quite general with how these whitelists are defined. One way one could do it is to have the browser vendors serve us blacklists. However, that would put all the emphasis on the browser vendors, and we're not sure that they actually want to do this. Another alternative would be to allow web pages to specify a whitelist in, say, the HTTP header, similar to the CSP. But nothing would prevent every web page to just say no extension is allowed to ever execute on my domain. And then we'd have to query the user a lot, because the user would be the one that should make the final call. Or a slightly more security-aware user can be allowed to classify web pages. And this is kind of an all-or-nothing approach, where you can classify web pages into sensitive and insensitive ones. And then you can have a policy that says that no extension is allowed to read data from any sensitive web page. And all extensions are allowed to read from all the insensitive ones. And we can also flip this around so that no web pages are allowed to probe for any sensitive extensions, but all web pages are allowed to probe for the insensitive ones. So for the long term, we think Latex Gloves, which is the mechanism that I just described, we think it's a good approach. We have a proof of concept prototype that kind of verifies that it is indeed possible. And in October 2018, Chrome mentioned that they actually start to have users allowed to change host permissions for their extensions, which basically means a user can now say that this extension should not be allowed to read data from this specific web page, which is kind of nice. But for the short term, the random UUID should be regenerated more often. For instance, every time you start the browser, that would limit potential tracking to per browser session. When you enter private browsing mode, then that random UUID should probably be regenerated as well, because private browsing mode in Firefox tries to block tracking scripts, but if they still allow you to have a perfect tracker based on your extension, then it doesn't really help. You could randomize the full URL for the extension, not just the ID. That would help. It's not perfect. But if we take the extensions that injected content, only 0.88% of those extensions only 0.88% of all the web accessible resources they had would uniquely identify a browser extension in that case, which basically means that you need to be lucky because you cannot probe. So they need to inject that specific resource. And extension developers should use data URIs more often. A lot of the web accessible resources are images. So if they use data URIs instead, then they don't have to have these extension URLs at all, which would help to mitigate the problem a little bit. And that's it for me. Thank you.
Hi, Ben Stock from CISPA. Thanks for the interesting talk. I'm wondering if it's possible to also identify extensions by the artifacts that they leave in the DOM and in the global JavaScript space. So if you have like some variables that are registered, it doesn't matter if it was because it was injected directly into the site or loaded somewhere. Do you have any idea in how many cases this could be used to maybe fingerprint extensions that are there?
No, we haven't looked into that. But we do know, I mean, past work has also shown that just not arbitrary, but DOM modifications that doesn't have a web accessible resource can also be used to uniquely identify browser extensions. Mm-hmm. And that is kind of what we want is that if you want to figure out which extension that is being executed, you need to do some sort of behavioral analysis. Mm-hmm. And that is the main goal for us. But we have not looked at whether or not they leave any variables that you can use and stuff like that.
And related to the data URLs that you were talking about, I think one potential problem is if you inject, let's say you want to load an image, then you load that image from an extension. That means the main page itself cannot read the content of the image due to the same origin policy. But I think if you inject it directly as a data URI, the website itself could read the actual content of the image and potentially even just by looking at the content of the image be able to uniquely identify the extension.
Yeah, that's probably true. Yeah.
Okay.